Hello everyone. Today's topic is about deriving Pauli spin matrices. Okay, so here we shall obtain Pauli spin matrices considering the all the ideas that we have learned in our last a few classes regarding with angular momentum operator, angular momentum states actually. So the angular momentum states are JM states, and corresponding to that states we have already obtained the matrix element of j square and jz. Now I am showing all these matrix element as because that these matrix element are required to obtain the Pauli spin matrices. Now here I want to tell you one thing, just I want to say you one thing, that this particular video I have made for you actually, and it is a continuation of our last class, but this video is also especially for NPTEL workshop. I am just attending a workshop on transition to online facilitation, and so this video is for you as well as for NPTEL workshop. So continue with this. I want to tell you that in those matrix element we have got h car square j into j plus 1 and delta of delta function canonical delta function, and those matrix element will exist for which j prime will be equal to j, m prime will be equal to m, and corresponding to each j value, that here j value will be 0, half, 1, 3 by 2, 2, 5 by 2, etc., and corresponding to each j value m is equal to minus j2 plus j. Now to obtain the Pauli spin matrices as it is related to spin, so here we shall deal with the j value is equal to half only. So corresponding to half, the matrix representation of j square and j square and jz can be easily obtained. Okay, so that particular for particular j is equal to half, m value will be minus half to plus half. There will be two particular states are there, half states and half minus half states. You see this is the half of states, and half minus half states. So corresponding to these states we have four matrix element. Okay, and among these four matrix elements only the first and the third matrix element will exist actually, because in these two cases, as you know, that in these two cases that m prime is equal to m that occurs. That's why this matrix element will exist actually, and corresponding to that particular value of j is equal to half, the matrix representation of j square will be like this. Okay, the first element, second element, third element, fourth element. So this first and fourth element will exist, and considering the eigenvalue solution of j square, we can obtain 3 by the matrix representation of j square is equal to 3 by 4 h car square 1001. Okay, so here you see all these matrix elements are real in number. Similarly, proceeding in the same way, we can obtain the matrix element of jz for j is equal to half. Remember that for j is equal to half, and we have already obtained the matrix element of j square and jz for j is equal to 1 also. Now here we are specially dealing with j is equal to half because we are to obtain the Pauli spin matrices. Okay, jz is equal to half h cut 100 minus 1. Fine. So here also we see that the matrix elements are real in number. Now therefore we can see that for j is equal to half, the matrix representation of j square is this one, matrix representation of jz is equal to this one. Okay, fine. Now can you tell me with the definition of Hermitian operator a is equal to a dagger, can you examine the hermiticity of j square and jz? Can you tell me whether that particular j square and jz can be Hermitian or not? Okay, so think about this. So hope in your mind you have find out the logic. Now these are Hermitian operators because j square will be equal to j square dagger and jz will be jz dagger. Okay, so from these two things we can say that these two operators are Hermitian operator. Fine. Now from the definition of our raising and lowering operator, j plus is equal to jx plus ijy, j minus is equal to jx minus ijy, where jx, jy, jz are the component of j actually. So the matrix element of j plus and j minus will be this one. Already these things we have already derived. So J plus is the raising operator because it raises the value of m by 1 unit up to 1 m plus 1, and J minus is the lowering operator because it lowers the m value from m to m minus 1. Okay, now those matrix element will exist for which m prime will be equal to m plus 1 and m prime will be equal to m minus 1. Fine. Now can you proceed with the same way? Can you find out the matrix element of J plus minus for J is equal to half, just like J square and Jz? Obviously we can find out. Okay, hope already you have find out that. So the matrix element of J plus will be h card 0 1 1 0 and J minus h card 0 0 1 0. Again we see that this matrix element of J plus is real in number and matrix element of J minus is real in number. Fine, very fine. Now whether this J plus and J minus are Hermitian just like J square and Jz, can we examine that? Or also is it possible to obtain J plus if we know J minus, and or if we know J plus can we obtain J minus, or if we know J minus can we obtain J plus? Answer is no. To the first answer there it is no, because these are not Hermitian. These are not Hermitian because J plus cannot be equal to J plus dagger and J minus cannot be equal to J minus dagger. But we have find that J plus will be J minus dagger. So if we and J minus will be J plus dagger. So if we know, you see, J plus will be J minus dagger and again J minus will be J plus dagger. So if we know one particular matrix element, we can obtain the other. So knowing J minus we can obtain J plus, and knowing J plus we can obtain J minus. Now from the definition of our this J plus and J minus, we have Jx is equal to this half of J plus and J minus, Jy is equal to 1 by 2 J plus and J minus. Okay, J plus minus J minus actually. So from this two definition, from this expression of Jx and Jy, we can find out the matrix representation of Jx and Jy in terms of J plus and J minus. So from this expression we can obtain that the matrix element of J plus will be addition of J plus matrix element and J minus matrix element. Matrix element of Jy is nothing but 1 by 2 I matrix element of J plus minus of J minus. Okay, so as we have already obtained the matrix element of J plus and J minus, we can obtain the matrix element of J plus and Jy from these two matrix element. Okay, and also we shall obtain the matrix of J plus and J minus. Now my question is, can you now easily obtain the matrix representation of Jx and Jy from the representation of J plus and J minus? Find it out, quickly find it out. From the addition of J plus and J minus, from the subtraction of J minus and J minus, J plus and J minus. So yes, from the addition of the matrices of J plus and J minus, we can obtain the matrix representation of Jx is equal to half of h card 0 1 1 0, and therefore Jy is nothing but 0 minus I 0. So here you see Jx is real in number, but Jy is complex in number. Okay, so we get the matrix representation of Jx and Jy, and earlier also we have obtained the matrix representation of Jz actually. Okay, fine. So what I want to tell you that let me keep it here. So what I want to tell you that here we have obtained the matrix of Jx, matrix of Jy, matrix of Jz. So this is the component of the angular momentum operator Jx, Jy and Jz. So this angular momentum operator, component of the angular momentum operator J are expressed here through the matrices 0 1 1 0 0 minus I 0 and 1 0 0 minus. Okay, so here I want to tell you that all these three matrices can be expressed as J is equal to half of h cut sigma. Okay, keeping this particular constant value aside, we have these matrices as we here representing by sigma actually. Now as here we are obtaining the value of the matrix for j is equal to half. So for j is equal to half, it is the angular momentum operator. So for j is equal to half, it is nothing but our spin angular momentum. Okay, so the s is equal to half of a squared sigma. Now we are telling that this particular sigma is nothing but our Pauli spin matrices. Okay, so Pauli spin matrices are nothing but sigma x, sigma y, sigma z. For jx will be half of a squared sigma x, jy will be half of a squared sigma y, jz will be half of a squared sigma z actually. So sigma x, sigma y, sigma z are these two by two matrices actually. Okay, these matrices sigma x, sigma y, sigma z are nothing but our Pauli spin matrices. Okay, so we have obtained the Pauli spin matrices considering the angular momentum representation of j square, jz, j plus, j minus, as well as that jx and jy. Fine. Now in the conclusion part, I want to tell you that for j is equal to half, we have obtained the matrix representation of jx, jy and jz, and correspondingly we have obtained the Pauli spin matrices sigma x, sigma y and sigma z. Okay, in my next class, in my next video lecture, we shall obtain the we shall study and obtain the properties of Pauli spin matrices, and also as we have done that part actually, we shall obtain the eigenvectors corresponding to each matrices. Okay, and we shall do this in our next class actually. So this much is for today. Let me stop here.